as promised, I found the time, and I'm going to give you another example problem dealing with the inclined plane. Seeing as how we didn't get through a whole one in class today, I wanted to give you another example so that you can work on some stuff this weekend, hopefully come back to class on Monday with a little bit better understanding of how we go about attacking this problem, et cetera, et cetera, et cetera. So here's an example problem that is a real life example taken over from the desk over on the side where I have the computer and stuff like that, that messy lab table where the computer is. But anyway, it says a 1,000 gram or 1 kilogram mass is resting motionless on a ramp that makes a 14.2 degree angle with the table. What is the normal force and the force of static friction acting on the mass? So if we go through and attack this problem the same way we always do, this problem is asking us for two things. It's asking us for the normal force, which we'll represent with blue, and then it's asking us for the static friction force, which we'll represent with red. Remember, static friction is that friction that is acting on things that keeps them from moving in the first place, or keeps them still. We'll review some static friction stuff as we go along. But those are the two things we're looking for. There's two pieces of information that we know in this problem. The first one is the mass of the object. It tells us that it's 1.00 kilograms, so you don't have to do the conversion from grams to kilograms. I did it for you. Hopefully you know that one now. And then it tells us that the angle theta in this problem is equal to 15 degrees, not bad, is equal to, oh, a little too big there. Sorry about that. So the mass is equal to 1 kilogram, and then the angle theta is equal to 14.2 degrees. And that's my cell phone down there. Because I'm a nerd, I have a protractor app on my cell phone, and that's the actual angle that the ramp is making with the table. So if we go to our picture, that means that this angle down here is 14.2 degrees. There's one more piece of information that we have that, even though it doesn't specifically say it in the problem, is going to help us solve this problem. And that's the fact that this mass is resting motionless on the ramp. That means we have equilibrium. And that means we got to satisfy these two conditions. Net force on the x-axis 0, net force on the y-axis 0. Those are still our conditions of equilibrium in two dimensions, even though now the ground is tilted. So the first thing I'm going to do is I'm going to take this picture out of that space so that we can draw a little bit more on it. Okay? So three forces that are acting on this mass. The first force, like we always do, we'll go the force of gravity. And there's the force of gravity. And the force of gravity is still equal to m times g, like we discussed. Okay? And in this case, that's pretty easy because the mass is 1 kilogram, so the force of gravity here is equal to 9.81 newtons. Now, there are two other forces that are acting on this object, okay? And these are similar to the things that we did before. So the first force that we can draw in is the normal force. Normal force represented in blue. We said that normal force, it gets its name from the fact that it's perpendicular to the surface that causes it. In this case, the surface that that object is resting on is the ramp itself. So the normal force has to go act perpendicular to that ramp. So I'll draw it in something like that. Although it's probably going to be more like, let's go like that. Okay? Then the third force that's acting on this object is the force of friction. If we look at both of these forces, even though they don't act parallel to the ramp, they're both sort of acting in a way that if the object was left with just these two forces acting on it, it would move towards the left in our picture. But that's not happening here. That object is not moving at all. That means there has to be a third force acting on that object. The only other thing that can influence that object right now is the fact that it's in contact with the ramp. There is a frictional force between the ramp and that object. And that frictional force, like we talked about static friction, always acts opposite of an applied force to result in zero net force. If both of these forces that we currently have drawn are sort of pulling us in this kind of direction. If these were the only two forces, we'd end up moving down the ramp. That means that the frictional force has to act up the ramp, something like that. Okay? So, first I'm going to get rid of this. Okay? And I'm going to first rearrange my forces a little bit, just so they're a little bit more. Actually, I'm going to bring in my x-axis and my y-axis. I made it yellow in this case, so it'll show up on the picture. That may choose to be a good choice or a bad choice. I guess we'll see. Then I'm going to adjust my forces a little bit so that they all originate from the origin, just like we did in the last problem. Now, as we discussed in the last problem, the way we would attack this problem in the past would be to break up the red frictional force, right, that being static friction, and the blue force coming from the ramp, that being the normal force. We would break both of them up into their components, just like this, right? There would be a horizontal red, a vertical red, then there'd be a horizontal blue, and a vertical blue, just like this. The problem being, with the way that our x and y axis is oriented right now, and not knowing the normal force or the static friction force, we don't have enough information to calculate those vectors, or those component vectors. So, in order to alleviate that problem, first, we'll get rid of these. Okay? And we said what we're going to do is not to try and find those forces, at least not originally, but we're going to play with our frame of reference, and that will help us. So we're going to take our x and y axis, and we're going to rotate it 14.2 degrees. And by rotating that axis 14.2 degrees, we end up with the normal force being on the x-axis and the static friction force being on, the normal force being on the y-axis and the static friction force being on the x-axis. Now we don't have to break it up into components, because forces that act along the axis in the problem don't have components. The only force right now that isn't laying on one of the axes in our frame of reference is the gravitational force, and that's this one. So now I'm going to get rid of this picture. So now we're only left with our forces. We're going to adjust some things a little bit. It's here. I'm going to move this just a little bit more so it looks like that. Now, we attack this problem just the way we attacked this problem earlier in all the other parts. We take any force that isn't on the x-axis or the y-axis and we break it up into components. In this case, that's the gravitational force. So the components always run along the axis system that we've drawn, or along the x-axis and the y-axis. That's why it's a horizontal component and a vertical component. So that means that green, the gravitational force in this problem, is actually doing two things. It's pulling down the ramp. It's pulling down the ramp, but it's also pulling into the ramp, just like that. Doing a little rearranging, we can take this parallel component, or the parallel component, or the component of gravity that is parallel to the ramp, and move it down here. Because that vector, that component vector that I just moved, runs along the x-axis, or the horizontal axis, and because this component, the one that I just highlighted, runs along the vertical axis, or the y-axis, we know that this has to be a right angle. That has to be, let's not make it a rounded off square, let's make it a square. So that has to be a right angle. Now we have a right triangle where we know one of the sides. Remember, I told you before that if we go back to this original picture, the angle between the ground and the ramp which we said was 14.2 degrees, we measured to be 14.2 degrees, is also equal, that's exactly the same angle as this angle right there. The angle between the gravitational force and the tilted y-axis. So we'll label that theta as 14.2 degrees. Now we have a right triangle where we know the hypotenuse, we know one of the angles, and we can go ahead and we can find the other sides. We talked about before that if you don't like the way this picture is, do this. Move it out of the drawing. All right? I'm going to take all this stuff with me. Move it out of the drawing. Never mind that. And just twist it and make it look like a right triangle. So it looks like this. The most important thing being, though, that the gravitational force, the solid green arrow, has got to be the hypotenuse of this triangle, because it's the force that we're breaking into components. The force we're breaking into components has always got to be the hypotenuse, because the other two forces run along the axis. They're the sides of the triangle. So the gravitational force always has to be the hypotenuse of the triangle. Now, you've got an angle, 14.2 degrees. You've got a hypotenuse. Use your trig identities and find the other two sides of the triangle. That's what I get when I do those two sides. So I'm going to group all these together now to keep them all together. I'm going to bring this back over to my picture, but I'm going to tilt it so that gravity goes straight down again. I'm going to tilt it a little more. It goes like that. Okay. Now, because this object is sitting motionless, we said there has to be two conditions that have to be met. Our two conditions of equilibrium, that being net force on the x-axis being equal to 0 and net force on the y-axis being equal to 0. If we take a look at the x-axis, that's this axis in the picture. Okay? There are only two forces that are acting on that axis. The red static friction force, and then the parallel component of gravity. If there are only two forces, and they have to add up to 0, if we know one, we automatically know the other one. And that means that the static friction force has to be equal to 2.41 newtons. On the other hand, the y-axis, that's the one that runs this way in our problem. Once again, we have to have equilibrium on that axis. There are only two forces on that axis. There's the normal force, and then there's the perpendicular component of gravity, perpendicular to the ramp itself. If there are only two forces on the y-axis, they point opposite directions and they have to add up to 0. That means that the normal force has to be equal to 9.51 newtons. A problem similar to the one we just did with the car on the ramp, or the car on the ramp of the trailer or whatever it was, but now that opposing force is being provided by the static friction as opposed to the cable that was attached to the car. But the concepts remain the same. We still have to have equilibrium on the two axes. All right, where does that take us? For today's calendar, or Friday's calendar, depending on when you're watching this, This link relates to the one that we started in class, but we didn't finish. It walks you through the whole problem, front to back, first introduction. Hopefully you've watched that one already. Where do we go now? There's 3 more problems that you can do in this here, okay? I gave you another example that was very similar to number 1. Number 3 is a little bit different. It's just a different form of equilibrium. If I'm not mistaken, number 3 involves something moving at a constant velocity. That doesn't change the way you do the problem. It's still the same, it's just a different form of equilibrium. So that problem you can do. Number 2, very similar to number 1, and it's one problem that we just did. And then number 4, more similar to number 3, but once again, the concepts stay exactly the same. This link that I added gives you answers to those problems, so you can see the answers and find out if you're doing them correctly. Hope this helps. I'll go over a little bit more in class on Monday. You can ask questions then.